You drop something, you watch it fall. It's super basic, right? It's one of the most fundamental things we experience. That constant, relentless pull towards the ground, that's gravity. But what's really happening when an object is falling? Well, let's get into it and break down the physics of motion under gravity.
Okay, so let's kick things off with a real head-scratcher, one that people have debated for centuries. Picture this. You've got a bowling ball and a feather. You drop them at the exact same time. Which one hits the ground first? I mean, our intuition just screams the bowling ball, doesn't it? It's heavier, it's more solid, it just feels like it should plummet faster. But is our intuition right?
This isn't a new question. To get to the bottom of it, we've got to rewind a few centuries to one of the most famous legends in science. The story goes that Galileo Galilei climbed up the Leaning Tower of Pisa to settle this exact debate. He dropped all sorts of different objects to prove to everyone watching that our intuition is totally wrong. They all fall at the same rate.
So what exactly did Galileo figure out? Well, the secret lies in understanding a state that physicists call free fall. It's what happens when gravity is the only force in the picture. So here's the official breakdown of free fall, and it's a really specific idea. When we say an object is in free fall, we mean that literally the only force acting on it is Earth's gravity. For now, we're going to completely ignore pesky things like air resistance. Just imagine dropping something in a total vacuum. No air, no friction, nothing. And here's the part that's kind of mind-blowing. In that perfect free fall, the acceleration is exactly the same for everything. It doesn't matter if it's a piano, a tiny pebble, you, me, anything. Near the surface of the Earth, it all accelerates downwards at about 9.8 meters per second squared. This number, we call it g, is the absolute star of our show.
And because g is this super reliable constant, we can actually predict how things fall with amazing accuracy. Now don't get bogged down by these formulas, okay? The big idea here is that this magic number g lets us calculate exactly how fast something is going and how far it's fallen at any point in time.
And this brings us right back to Galileo's huge idea and our first question. If the acceleration is the same for every single object, then it just doesn't matter what it's made of or how big it is. That feather and the bowling ball? Yeah, in a vacuum, they land at the exact same time. No question.
Let's put this into practice. Imagine a car falls off a ledge. It's not moving at first, right? So its initial velocity is 0. Let's say it falls for just half a second, and we know its acceleration is g. We'll just round it to 10 to make the math easy. So what's its final speed? We just use that first equation. 10 times 0.5 gives us 5 meters per second. See? Super straightforward.
Okay, wait a second. If an object's mass doesn't affect how fast it falls, then what's the deal with mass versus weight? I mean, we use those words all the time, pretty much interchangeably. But in the world of physics, they are totally different things.
Let's just break this down. Mass is basically how much stuff you're made of. It's the matter inside you. Your mass is your mass, period. It's the same on Earth. It's the same on the moon. It's the same if you're floating out in deep space. But your weight? That's totally different. Your weight is just the force of gravity pulling on all that stuff.
And this little formula here, W equals m times g, connects everything perfectly. Your weight, W, is just your mass, m, which never changes, multiplied by whatever the local gravity, g, happens to be. So you can see right away, if g changes, your weight has to change along with it.
So let's nail down the key things about weight. It's a force, right? We measure it in newtons. It always pulls you straight down toward the center of the planet. But here's the big one, the one to remember. Because the formula for weight has g in it, and g isn't the same everywhere in the universe, your weight can change.
Now this whole idea that your weight can actually change, that's pretty wild, isn't it? So, let's take a little field trip. Let's go somewhere where gravity is way different and really see this in action. Come on, let's go to the moon.
So, why is gravity so much weaker on the moon? It's all in the numbers. I mean, just look at the difference. The moon has way less mass than Earth, and it's a lot smaller too. You put those two things together, and what you get is a much weaker gravitational pull, a much smaller value for g.
Okay, so how much weaker are we talking? Well, after you do all the complex math, it actually boils down to a really simple, really famous fraction. The pull of gravity on the moon is just 1/6 of what it is here on Earth.
And that leads us to this really direct, really powerful conclusion. Since your weight is just your mass times the local gravity, an object's weight on the moon is going to be, you guessed it, exactly 1/6 of what it weighs right here on Earth. let's make this concrete. Say you have something with a mass of 10 kilograms. Here on Earth, it weighs 98 newtons. Now you take that exact same object, fly it to the moon, and suddenly it only weighs about 16.7 newtons. The amount of stuff is the same, but the force pulling it down is way, way less. And that's exactly why you see those old videos of the Apollo astronauts just bouncing around up there.
All right, we have covered a ton of ground, from a tower in Pisa all the way to the surface of the moon. So let's wrap this up and really lock in the most important takeaways from our little explainer here.
Okay, if you walk away with nothing else, I want you to remember these 3 things. First, in a vacuum, everything, and I mean everything, falls at the same rate. Second, your mass is constant, but your weight changes depending on gravity. And third, the moon's gravity is only 1/6 that strong, so things weigh a lot less up there.
All right, let's do one last little pop quiz to see if you've got it. Based on everything we just talked about, if an object weighs 10 newtons right here on Earth, what would it weigh if you put it on a scale on the moon? Go on, take a second to think about it.
If you said 1.67 newtons, you nailed it. Absolutely right. You just take the Earth weight, you divide by 6, and boom, you've got it. And just like that, you've used a fundamental law of physics to figure out what it would be like on another world. Pretty cool, right? It just goes to show you that the rules of the universe are the same everywhere. They just play out a little differently depending on where you are.